In this video, we're going to continue our discussion on a sampling distribution, but more specifically, I'm going to show you how to calculate the standard deviation given a sampling distribution. First thing we're going to do is use our previous example of this statistic over here, which explains how many Americans at this point in time are very worried about the COVID-19's effect on the economy. And we used 57.2% as a starting ground. So the first thing let's do is let's go back to our website of the Rossman Chance here applet collection. And just to show you again how to get to this website, you go to rossmanchance.com/applet, and then you click on this link right here, the one proportion inference. Okay, when I click on that, you'll have a couple options. All right, and instead of using the heads and tails simulation, we're going to use whether you agree with the statement or not. So I'm going to change this 0.5 to 0.572. All right, we sampled 1,000 different households. So we're going to keep this at 1,000. And we did approximately 4,500 samples last time. Okay, so we're going to click on 4,500 different samples. We don't need to animate them. And we're also not interested in the number of successes, but rather the proportion of successes. So we're going to click on that. Leave the normal approximation off for now, but if we've done everything correctly, we should notice that it takes on a roughly normal distribution. So let's do that. Let's click on Draw Samples and see what comes up. It's going to take a little bit of time. But notice how, again, we see a roughly normal distribution, a normal curve that is centered at, you guessed it, 57.2%. So we're in good shape. Now, for most of us, the 57.2% as the middle is very easy to see, right? We see it right here. But then the range or the standard deviation is a little bit more difficult to get it exactly, okay? If you can pull from this that it looks like the standard deviation is approximately 1%, I'm totally fine with that. I think using your graphics and your visuals as a way to help you understand a concept is more important than getting the technical, accurate, correct answer. So if you look at this and say, okay, it's a normal curve with a mean of 57% and a standard deviation of 1%, as your instructor, I'm very proud. All right. Now, if you want to get that number exactly, how do we do that? Here's what I want you to click on. All right. Actually, the first thing I want you to do, it might take us a little bit of time, but I want you to take a mental image of this curve, right? I want you to notice how there looks to be a pretty high peak here at 57, a pretty high peak here at just below 57, but for the most part, that general same curve. Because what I'm going to do, and again, I don't want to waste your time, but I'm going to re-simulate this whole thing. I'm going to do 4,500 over again. And you should notice a little bit of difference, okay? So again, I'm looking at this peak right here. I'm looking at this peak right here. I'm noticing this little notch here at 54. If I do it again, I should notice the outline. Think of a city skyline. It's going to be a little bit different, all right? So let's do that. We're going to go back up here to the top. We're going to click on Reset. Let me zoom back out so we can see everything on the same screen, okay? So we're going to click on Reset, and all of that goes away. Let's do it one more time. Click on Draw Samples, and notice the differences here, okay? And what I want you to first recognize is those peaks that we saw earlier, I don't necessarily see them as drastic. That little notch I saw at 54% is it's not even there. But what else do you notice about this? And this is something I wasn't even expecting until we just did this here right now. Look at the scale. Notice how we go from 57 to 59, then we go to 60, then we go to 62, then we go to 63. Go backwards in this direction, we go from 57 to 56 to 55. It's a very inconsistent scale. And I'm not saying this to Rossman Chance, wherever you are out there. I love your website. I think it's great. I'm not nitpicking. But it also lends the opportunity for us to say, okay, maybe the scale, while it's a good place to start to estimate the standard deviation, it sometimes gives us conflicting results. Even if it's only a fraction of a percentage, it can sometimes mislead us. All right. So I think now the importance is, how do I really figure out what this standard deviation is? Okay. Well, I'm not going to ask us to create another one because, again, your time is valuable. My time is valuable. Let's work with what we have. But I'm going to ask us to click on this normal approximation here. And again, that's going to bring up a blue silhouette of what this curve should look like. Okay, and notice how, again, there's not much overlap, which is good. There shouldn't be. It means what we experimented lines up pretty much with what a normal approximation would be. Okay, now the next thing I want you to do, this thing we haven't clicked on. Why doesn't he click on summary stats? This whole class is built off of stats. Why don't we just click the darn summary stats? And it'll give us the standard deviation. And guess what? It does, right? It gives us our mean of 0.572, and it gives us our standard deviation of approximately 1.5%, 0.016. So from here, most of you might say, well, just to get the standard deviation, as long as I do this website and I click on summary stats, I'll get that number and I'm good to go and I'm golden. And you're right. But how does the computer come up with that number? And that's what I'm going to show you. So remember this 0.016. I want to go back to Microsoft Excel or Google Sheets here to help explain that. So the standard deviation is equal to, again, 0.016. Our mean is equal to 0.572. And is there anything else that we can gather from this? Our sample size was 1,000, and we had 4,500 different samples. Okay, and I'm just making think of this as a key. Right, this is all the information I have right now. Now, to come up with the standard deviation, all right, let's highlight this guy so we don't get confused with the others. I'm going to use to some degree these two numbers actually. So I'm glad I listed these. The 4,500 doesn't really help us here, okay? But the 1,000 helps us and the mean. And there's a formula for standard deviation of a percentage that looks something like this, okay? It's going to look like the standard deviation is equal to the square root of p times 1 minus p all over the sample size, okay? Now, if you're like me, I look at that and that's, I don't know, a little confusing, all right? Let's try to find a better way to format that. Okay, let's go back a little bit here and I want to find where our AP statistics packet is, because that actually has a nice way of formatting that equation. Here we go. And this you could find anywhere online. I find it as a very useful tool as you're completing your AP course, whether you're in high school or in college. Now, if I go down here, I want you to locate this formula. I'm trying to highlight it here. Let me zoom in a little bit. And now, when I teach statistics, I try not to use symbols that much. If I'm teaching AP Stat, that's a different story. But if I'm teaching an introductory level statistics class in college, my whole thing is practicality, over technical terms. Okay, so what I'd like you to interpret this as, when we look at this lowercase sigma, what that means is standard deviation. So the standard deviation of, let's interpret that little p hat, what that means is a sample proportion. So the standard deviation of a sample proportion, which we have in this case, is equal to the proportion times 1 minus the proportion over the sample size, okay? So what that means for our example is 0.572 times 1 minus 0.572 all over 1,000. And if I take the square root of that, I'm at my standard deviation, all right? So let's go back. Here we go. Again, standard deviation is equal to, well, let's first do this. Let's find 1 minus 0.572 first, and I get 0.428. So these are the two numbers I'm going to use, all right, in my equation. So let's make this a little bit bigger so we can see this. So standard deviation is going to be equal to the square root of, I'm going to put another parenthesis in there, 0.572 multiplied by 0.428 end parenthesis, and then divide by 1,000. Then press enter, and you notice we get 0.015646, and if I round that to the nearest thousandth, I'm going to get 0.016. Okay, so if you're, again, looking for the formula, how that looks, right up here in the formula bar, 0.572 times 0.428 divided by 1,000. Okay, if you ever forget that formula and you forget how to do this part, one recommendation I always have for students is to think about the numerator. Let me go back to this equation here real quick. If we know something about our decimals, okay, and I want you to think about maximizing that numerator. All right, what percentage will do that? Okay, and I'll give you a hint. We were pretty close with 57.2%. Okay, here's another way to think about it. If the percentage was 0.10, okay, if I did 0.10 times 0.90, I'm going to wind up with 0.09, right? As I get closer and closer to these two values being the same, that product is maximized, right? Which is not, again, entirely too important to know. But if I were to plug in 50% times 50%, I'll get a numerator of 25%. That's the highest that numerator could ever be. It maximizes the top half of that fraction. So when we're dealing with a measure where it's sometimes better to be conservative and to estimate it as a larger number, why not just use that large estimate as your default, like for every single problem? What does he mean by this? What's he talking about? So let's say in this case, I didn't know it was 57% or 42%. If I type in equals the square root, okay, and I follow the same process, start the parentheses with 0.5 times 0.5, close those parentheses, and then divide it by 1,000, what you should notice is you get pretty much the same answer for all practical purposes, okay? It's not much difference. So in this equation, and I always go back to this, when we talk about measures of variability, and standard deviation is one of those, right? Because it's the square root of variance. It's always dependent mostly on the sample size. These, I'm going to highlight these in orange. No hate against the color orange, but they're not as important as the green. That gives us the gas, gives us the go. N equals 1,000. That's the reason our standard deviation is either high or low relative to how you think about it. So now that I have this standard deviation, okay, let's go back to our curve here. Now I have these sample statistics. I can use them to answer questions like, what's the probability I get a sample that answered greater than 60% to this question? Okay, I can use z-scores to do it. I can even use this website to do it, right? If I click on this thing here, proportion of successes as extreme as greater than or equal to, we'll say 0.60, and I click on count, notice how it gives me that probability right away. It shades in the region. It gives me the z-score. It gives me now the p-value is something we'll talk about more with significance testing, but for now, I want you to associate it with the percentage or the likelihood. So the likelihood that I get a sample over 60% is 3.68%. Okay, and I can use this all day. Okay, if I wanted to say that now I want less than we'll say 0.55, right, or 55%. We click on that. Now my z-score is negative 1.41, and I have a 7.99% chance of getting a sample that is that low. All right. So, long story short, here you have your standard deviation. Now I can go play, meaning I can go use these two numbers, mean and standard deviation, in 68, 95, 99.7 rules, or z-scores. Okay, hope this helps.